Thank you, and thank you for invitation and this nice opportunity to give a presentation in this audience. So I will talk about the ultrafast dynamics in antiferromagnets, but it's a very special dynamics which is related with the entangled states. And the take-home message of my talk is that light can induce some macroscopic quantum dynamics in antiferromagnets, and this macroscopic quantum dynamics is the entangled states of two-magnons mode, which is a very specific feature of the quantum systems itself. So why we are interested in this ultra-fast things, Rostislav has just explained that our technology, which is now in nanoscale, works at the nanosecond time scale, will be changed in the nearest future to the faster processes. But when you want to develop technology, you need to have a good science for this. And while the nanosecond technology can be associated with a classical description of the magnetic systems, in which the moments of magnets are almost in equilibrium, then once we try to go to the femtosecond range, we step in terra incognita. So we are at the time and energy scales when the classical regime can be substituted by the quantum one, and we need to know how to control and manipulate this. And a very nice playground in this case is an antiferromagnetic system. Why? Because the antiferromagnets, as again, I think Rostislav, you made half of my job. As it was explained, antiferromagnets show high frequencies which fall into terahertz range. And for example, if we look at the magnon spectrum of the chrestomatic antiferromagnet potassium nickel fluoride, then we see that the frequencies of magnons, so internal frequencies of the system, can range up to 10 terahertz, which fits very well to this 100 femtosecond time scale, which we want to study. So in my talk, I will discuss the properties of these materials, which were studied experimentally by David Bossini and colleagues from Nijmegen. So Rostislav is also a co-author of this paper. No? Okay. So I was, maybe I do not know not everything. Okay. But anyhow, I will discuss the problems which we faced after the experiments. So the experiments were done on this potassium nickel fluoride 3 and its pump probe experiments, when the crystal is illuminated with a very short pulse, optical pulse, duration of tenths of femtoseconds. And after that, we probe in fact, the magnetic property of the system. So, initial pulse, and then we see some dynamics, some oscillations, which are associated with the spin-spin correlations in the system. And observation of these oscillations was a great, not observation, but interpretation of these oscillations was a great problem, which we tried to solve. And what was the problem? We can translate these oscillations into the language of the magnetic vectors. The antiferromagnet is described by two sublattice magnetizations, and these oscillations correspond to longitudinal oscillations of the antiferromagnetic vector of the system. And this was strange for theoreticians, at least for phenomenologists, because in phenomenology, we use to the classical description of antiferromagnetic dynamics. We use this Landau-Lifshitz type equation, and it works well in many cases. But the problem is that the classical oscillations of antiferromagnetic system are always followed by appearance of non-zero magnetization. And you cannot avoid this. This is the essence of the mean field approximation and this Néel approach to the sublattice magnetization. But this means that if the dynamics would be classical, we should observe not only longitudinal oscillations of antiferromagnetic moment, but also transversal magnetization, which should oscillate at the same frequency. However, our experiments showed that no magnetization can be attributed to the experimental signal. And this means that the classical approach based on Landau-Lifshitz and macroscopical long-range fields does not work. So we need to look for some different interpretation, and we started from the physics of the processes which was behind these pump probe experiments. And this physics is very well known for more than 50 years. What happened in the crystal illuminated by the light, we have a Raman process. And this Raman process is a simple conversion of one photon into two magnons. And this process implies that we have two conservation principles, one of linear momentum, so the magnons should propagate in opposite directions, and the other one, the conservation of spin, which means the magnets have opposite spin polarization. And such a process can be strong only in antiferromagnets, which have two equivalent magnetic sublattices. And again, this process was described very well by Fleury and Lockwood, we know the Hamiltonian, which is responsible for this process. And in our experiments, this light can be considered as the external field, which is applied during a very, very short time, so can be described by delta function. But what is important, and this was also known from 60s, that this kind of interaction, when translated on the language of the magnetic system, can be represented as a modification of exchange between neighboring spins. But this modification is very special, and it is space-dependent or anisotropic. So in other words, light modifies exchange interactions only in the direction which is parallel to the polarization of the incoming light. So the action of light on the system can be explained by this string model. So if we look at the exchange interactions as springs which couple two neighboring atoms, then before the pulse, the strength of the springs is the same in all directions. Once you apply the pulse, you change immediately, for a very short moment, you change the strength of the strings, but only in one direction. And what happens then? If the system was in equilibrium, nothing will happen, because then you see if this atom was in the middle, the only thing which changes, he feels different forces, but these forces are all equilibrated. But if by chance the central atom was a little bit deflected, so if we had some fluctuations in the position, then the energy of these strings which the energy of these new strings will be released through the oscillations of the system in a different direction, and this means creation of magnons. So we need to work with magnons, and which part of the spectra should we consider? So here you see again the spectrum of the potassium nickel fluoride, and it includes magnons with different K vector. But the point of antiferromagnetic magnonics is that the magnons with different K or different wavelengths have a very different structure. So if we look at the magnons, which corresponds to the center of brilliant zone, so these long wave magnons, which are classical things, these magnons involve oscillations of both magnetic sublattices. So they could be described as a classical rotation of the Néel vectors as well. But the magnons at the edge of the brilliant zone have very different properties. These magnons are mainly localized on one of magnetic sublattice. And this means that these properties, quantum properties of these magnons are much more pronounced, and they are more fitted for interpretation of our experiments. So this magnon mode, which corresponds to the edge of the brilliant zone, can be viewed as follows. So one sublattice, this violet, that does not move at all, and the other sublattice oscillates, and this is one mode. But in antiferromagnets, we usually have two modes, which are degenerate. So on top of this, we have another mode, which corresponds to the oscillations of the violet spins, while the red spins are immobile. And these two magnon modes are different systems, different particles, though they are very, very similar and have the same energy. So in the system, they are equally populated. But once we have these two magnon modes, which are very similar but still different, then we can interpret our light-matter interaction as follows. So light excites these two modes simultaneously, the modes with opposite K, in order to satisfy the conservation of momentum, and also these modes have opposite values of spin, and then the conservation of spin momentum is also fulfilled. And from the naive consideration of this picture, we can assume that once we have this light pulse, it simply induces two magnons, and that's all. And two magnons are not a quantum system. You can always describe them on the classical language. But the story is not so easy, so straightforward. So first we started to look at the dynamics of this system from the quantum point of view. And what we found out, we solved equation, Schrödinger equation of motion for the system. And we found out that the dynamics which is induced by light is not linear, in the sense that when you excite something, it's equivalent to rotation of the wave to the vector of state of the whole system in the Hilbert space, which is multi-dimensional. And this rotation depends, the angle through which you rotate depends on the frequency of magnons and also on the interaction constant between light and magnons. So the dynamics, in fact, is nonlinear because of the quantum nature of the system. And how we understood that this is a rotation, this certain type of rotation, we have noticed that the dynamics of this system can be described in terms of three operators, Kz, K plus, and K minus. These operators are two-magnon operators. They are proportional to the creation or to the pairs of two-magnon operators. And the most important thing that these operators, they describe rotation in some special space. So they are equivalent to the spin operators, and you know that spin operators are generators of the rotational group in the Euclidean space. So they describe rotation of the sphere, but these operators, they are called Perelomov operators and Perelomov states. They describe rotation in a more complicated space, and this is related with the opposite signs in these commutational relations. So we know that the dynamics of our system is somehow related with these operators, and then it is very easy because everything which concerns these Perelomov operators was described in literature again 50 years ago. Our task was only to read attentively the papers of old authors and translate it from Russian into English. So the states which so the space which is created by these Perelomov operators is very similar to the states which we know very well from optics. So in optics, we work with coherent states. So coherent state is a state of a minimal uncertainty, or coherent state is a state which you can obtain in the laser beam. But from the point of view of this formal quantum mechanics, coherent state, here is mistakes, here should be 0. So this coherent state is obtained by the same rotation in the Hilbert space from some vacuum state, and this coherent state can be represented as a superposition of this Fock states with different numbers of photons. So what we found out that the states which we get due to this pumping of light in the antiferromagnetic systems are very similar states called Perelomov states, and these states can be represented as a superposition, coherent superposition of the Fock states. But these Fock states are not single particle states. These Fock states are biparticle states, and they include excitation of the magnons from two modes with spin up and spin down. So the state which is excited by light is by definition an entangled state of the magnetic system. And I stress that this entanglement comes from the physics of excitation, because we have a process with one photon, two magnons, and the process in which you have some conservation of momentum and spin. So you do not know how the spin will be separated between two parties. And this state, entangled state, is a dynamical state. So this mu, coefficient mu, is a time-dependent value. It oscillates with the doubled frequency of magnons, and the amplitude of oscillations V is proportional to the intensity of incoming light. And this cartoon, I tried to show the entangled state, and it's very difficult because it's something quantum, but you see that the arrows disappear and appear. So when they disappear, this is a vacuum state 0, 0. When they appear, this is a state with one magnon. So it's a very complicated dynamics. And what is also important, this mu is the complex variable. So somehow it's a classical variable. You see, it depends on the incoming light intensity, and it's related with the frequency and other parameters. And this means that this parameter mu, it also describes the state of the system. So in order to describe the light-matter interaction of an antiferromagnet, we cannot limit ourselves only with the Néel vectors. We need to introduce more parameters which take into account the quantum degrees of freedom. What is also important with this light pulse excites these Perelomov states with different k. So in fact we excite not only one pair of magnons, we excite all modes which can be in the system, or all modes which respond to this signal. And this makes a problem, because if you have single mode signal with 1k, you have very well specified frequency and phase. But if you have many k's and the phase is k dependent, then how can we observe this crystal in macroscopic experiment? But the question, the answer is rather simple. So what we observe in the experiments, we observe excitations of the pairs of magnons which belong to the edge of the Brillouin zone. And here in this region, the dispersion, oh, what I have done? Okay, sorry. The dispersion of magnons is very, very low. This means that the femtosecond pulses of light excite these different magnon modes, but all the modes have almost the same frequency and also almost the same phase. And this is equivalent somehow to the driving of the laser excitations. So the light, external light, excites different modes with the same phase at T0. And then the oscillations, the relaxation of these modes proceeds with the same frequency and phase. And due to the interference of the signal, we can observe macroscopic signal in the experiments. Then here you see the signals which were observed in the experiments in at different temperatures. And frequency fits very well with that predicted. So this is a double frequency of the magnons from the Brillouin zone H. And then we studied temperature dependence of the oscillations. And this gives us another proof that the magnons which participated in these oscillations come from the edge of the Brillouin zone. How we see this? So these magnons at the edge of the Brillouin zone are related with the short-range interactions between nearest atoms, magnetic atoms. And if you look at the temperature dependence, you see that the amplitude of the signal is almost temperature independent, while the magnetization, sublattice magnetization, vanishes in the vicinity of the nailed temperature. So this means that the oscillations which we observe in the experiment, they are insensitive to the long-range ordering. And it's quite reasonable that once you have excitations which are related with the short-range interactions, which are not destroyed by the temperature, you will observe it even at the temperatures at which the antiferromagnetic order is almost vanished. And yeah, So to conclude somehow, we introduced in additional degrees of freedom which describe antiferromagnetic dynamics at the very short time scales, and these degrees of freedom take into account this quantum nature of antiferromagnetic ordering. And the parameter mu, which describes these degrees of freedom, it can be used to generate additional equations of motions which describe the dynamics of an antiferromagnetic at very short time scales. And what is interesting, this equation can describe very well the other experiments made by David, the experiments which shows the interference of the two pulses. So the idea is that instead of one pump pulse, we have two pump pulses which are separated by a certain time interval. And this means that this function in equation of motion consists of two peaks at different time values. So we solved this equation of motion assuming that we have two pulses with a time delay of t large. And what we get that this outcoming signal should have additional coefficient in amplitude, and this coefficient depends on the relation between time delay between the pulses and the period or the frequency of oscillations. So what we see in the experiments, this is a single pump pulse, and these are two pulses with two times delays. So this corresponds to the constructive interference with this cosine squared is 1, and this pulse, which is has half of the time delay compared to the constructive interference, shows destructive interference, so no signal. So this formalism somehow can be used, and its prediction is quite consistent with the experimental observations. And to end my talk, I would like to make some comparison between different states, quantum states, which we can found in different regions of different fields of physics. So when we are talking about this quantum information technology and other applications, we are usually talk about the photons and coherent states, and all this quantum cryptography is based on application of the coherent photon states. Moreover, this cryptography uses not only the simple coherent state, but coherent entangled states, when you can generate pairs of photons which belong to different modes. And in our case, we work with the magnon coherent entangled states. So they are very similar to the photon states, but still different. Mathematically, you can see it immediately from these factors before, but they are also very different in physics. And this table shows a comparison of the main properties and definitions of these coherent states of photons and magnons. So coherent states in photons, for photons, are defined in different ways. So if you open the textbooks, you can find one definition as states which correspond to the minimal uncertainty. And simultaneously, the same states are eigenstates of annihilation operators for photons, and these states can be also generated by some displacive operators and so on. But if we look at the magnon coherent states, they are much more interesting and much more rich. First of all, they are not correspond to the minimal uncertainty. So the minimal uncertainty will be only for certain values of this parameter mu. They are still eigenstates of annihilation operators, but their mathematical background which describes these states is very different compared to this Glauber technique, and I think that in application to magnons it needs more work. And at this point I came to the conclusion. So we demonstrated that the light can excite two magnons belonging to different modes, and these magnons are entangled. And what is more important, this entangled state can be observed in a macroscopic experiments. And with that, I end my talk. This is the title of the paper which we submitted, and which includes all this material. And here you can see the collaborators, so the co-authors, which we have a lot of them. So you can find it in archive. And I thank you for your attention.